There's a region of space so empty that if our galaxy existed there, humanity wouldn't have discovered other galaxies until the 1960s. We're talking about voids so vast, they make the distance between galaxies look like neighboring houses. And here's what keeps astronomers awake at night. These voids are growing, actively tearing apart the cosmic web that holds our universe together. Right now, as you're watching this, invisible forces are stretching space itself, not just moving galaxies apart, but creating expanding bubbles of nothingness that dwarf anything you can imagine. We're going to explore what these cosmic voids actually are, why they're spreading, and what it means for the ultimate fate of everything that exists. When you look up at the night sky, you see stars, lots of them. This creates an illusion that space is densely packed with matter. But zoom out far enough, and you discover something unsettling. The universe isn't evenly distributed at all. Instead, it resembles Swiss cheese, or maybe soap foam. Galaxies cluster along thin filaments and walls, surrounding enormous regions of almost nothing. These aren't just gaps between galaxies. They're structures so large they challenge our ability to comprehend scale. The typical cosmic void stretches 30 to 300 million light-years across. To put that in perspective, our entire Milky Way galaxy is only about 100,000 light-years in diameter. You could line up 3,000 Milky Ways across a single void and still have room left over. But calling them empty isn't quite accurate. Even the most desolate void contains about 15% of the average matter density of the universe. That might sound like a lot until you realize it means these regions are 85% emptier than empty space should be. Voids have a mean density less than 1/10 of the cosmic average. They're not vacuum in the absolute sense, but they're as close as nature gets on these scales. The discovery of these structures fundamentally changed cosmology. In 1981, astronomer Robert Kirshner was conducting a survey of galactic redshifts, trying to map the large-scale structure of the universe. What he found in the constellation, Boötes, stopped him cold. A spherical region of space, roughly 200 million light-years in radius, containing just 60 galaxies. Based on the density of galaxies in surrounding regions, there should have been about 2,000. This became known as the Boötes Void, colloquially called the Great Nothing. Its center sits 700 million light-years from Earth. And here's the part that makes you question your place in the cosmos. If the Milky Way had formed at the center of this void, instead of where it actually is, our entire understanding of the universe would have been delayed by decades. We wouldn't have had the telescopes powerful enough to detect other galaxies until the 1960s. Think about what that means. All of human history, all our myths about the cosmos, all our early astronomy, would have occurred while staring out at essentially nothing beyond our own galaxy. The universe would have appeared far smaller, far lonelier, far more mysterious than it actually is. We got lucky with our cosmic address, but the Boötes Void isn't alone. It isn't even the largest void we've discovered. That distinction belongs to the Eridanus Supervoid, a massive cigar-shaped region 1.8 billion light-years wide. Its center is located about 2 billion light-years from Earth, making it the dominant underdensity of matter in our galactic neighborhood. This thing contains about 30% less matter than the surrounding regions. What makes the Eridanus Supervoid particularly interesting is its connection to something called the CMB cold spot. When astronomers mapped the cosmic microwave background radiation, that faint afterglow from the Big Bang that fills all of space, they found an anomaly. A region of the sky that appears unusually cold compared to the average temperature. This cold spot is about 70 microkelvins colder than the average CMB temperature. At some points, it drops to 140 microkelvins below average. For years, scientists debated what could cause this. Then they discovered the Eridanus Supervoid sitting in the same direction. The connection isn't coincidental. When radiation from the early universe passes through a supervoid, it loses energy. The void's gravitational pull is weaker than average space, so photons climbing out of it experience less resistance. This creates a temperature deficit in the cosmic microwave background. The supervoid essentially leaves a shadow in the universe's baby picture. Now here's where it gets personal. You might be living in one. The KBC Void, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, is an immense region, roughly 1 to 2 billion light-years in diameter. And according to current observations, the Milky Way sits near its center. This creates a massive problem for cosmology. The standard model assumes matter is more or less evenly distributed throughout the universe. You can't just have a billion light-year underdensity with our galaxy conveniently placed in the middle. Yet that's exactly what the evidence suggests. Some researchers think this might explain one of the biggest mysteries in modern cosmology: the Hubble tension. The Hubble constant measures how fast the universe is expanding. When scientists calculate it using observations of the cosmic microwave background and baryon acoustic oscillations, they get one number, about 67 to 68 kilometers per second per megaparsec. When they measure it using galactic supernovae and Cepheid variables, they get a different number, about 72 to 75. These methods shouldn't disagree, but they do. What if we're inside a void? Galaxies within a void experience gravitational pull from the denser regions outside. This creates a local outward flow that makes the universe appear to expand faster than it actually does on average. You can think of a supervoid as having concentrated negative mass. It exerts a repulsive gravitational effect, raising the redshifts of galaxies beyond what cosmic expansion alone would cause. The theory method averages the Hubble constant over the entire universe. The observational method only calculates it within the KBC Supervoid, where we happen to live. If the KBC void is real, it would make our local measurements higher than the universal average. This could solve the Hubble tension. It would also mean our view of cosmic expansion has been skewed by our location this whole time. But voids aren't just passive features of the cosmic landscape. They're not empty bubbles sitting still in space. They're growing, actively expanding, and they're doing it faster than the regions around them. This happens because of how gravity works at cosmic scales. In dense regions where galaxies cluster together, gravity wins. It pulls matter closer, fighting against the expansion of space. But in voids, where density is already low, cosmic expansion dominates. There's not enough matter to generate sufficient gravitational attraction. Space stretches faster than matter can accumulate. Over time, this leads to increasingly large and empty regions. The voids grow by draining matter from their interiors. Any galaxy unlucky enough to form inside a void gets pulled toward the denser walls surrounding it. This creates a feedback loop. Less matter means weaker gravity, which means faster expansion. which pushes the remaining matter outward even more effectively. The void evacuates itself. Imagine you're standing in a crowd of people. Everyone is slowly shuffling away from you in all directions. At first, there are still people nearby. But as they move farther out, the space around you grows. Eventually, you're standing in a clearing. Then that clearing expands into a field, then a desert. The people at the edges keep moving away, and new empty space keeps appearing where they used to be. That's essentially what's happening inside cosmic voids, except instead of people, it's galaxies. And instead of a field, it's hundreds of millions of light years of increasingly empty space. This process is driven by something we still don't fully understand: dark energy. About 68% of the universe is made of this mysterious stuff. We can't see it. We can't detect it directly. But we know it exists because of what it does. It makes the universe expand at an accelerating rate. Einstein predicted this, sort of. He proposed that empty space itself could possess energy. Because this energy is a property of space, it wouldn't dilute as space expands. Instead, as more space comes into existence, more dark energy appears with it. This creates a runaway effect. Expansion generates more space, which generates more dark energy, which drives more expansion. For a long time, cosmologists assumed dark energy was constant, a fixed property of the vacuum. But recent data from the Dark Energy Spectroscopic Instrument suggests something more complex. Dark energy might be changing over time. The measurements indicate it was stronger in the distant past than it is now. The parameter scientists use to describe dark energy, called W, appears to have been lower than negative 1.4 billions of years ago. Today, it's closer to negative 0.8. This is bizarre. It suggests dark energy isn't just a cosmological constant, but a dynamic field that evolves. If that's true, it has profound implications for the ultimate fate of the universe, and it changes how we think about voids, because voids are where dark energy does its most important work. In dense regions like galaxies or galaxy clusters, gravity dominates. Dark energy is present, but its effects are overwhelmed by the gravitational attraction of all that concentrated matter. The accelerated expansion of the universe doesn't occur inside these dense structures. It occurs in the voids. The vast empty regions between galaxy filaments are where dark energy's influence becomes dominant. Without significant matter to counteract it, dark energy stretches space unimpeded. The voids expand faster than the cosmic average. They press against the surrounding cosmic web like inflating balloons. Over time, they push the filaments and walls farther apart. This means voids aren't just empty. They're active agents in cosmic evolution. They're the regions where the universe's expansion is actually happening. The intricate network of galaxies, clusters, and filaments that astronomers observe today is temporary. As dark energy pushes space outward, the voids grow. They stretch the cosmic web. Eventually, they'll tear it apart completely. The timescale for this is enormous. We're talking billions of years. But the process is already underway. In about 100 billion years, distant galaxies will be pulled away from us so fast that their light will never reach us again. The cosmic horizon will shrink. Future astronomers, if they exist, will look out at a much lonelier universe than we see today. Beyond that, the fate depends on what dark energy actually is. If it remains constant, the universe will experience heat death. Stars will burn out. Matter will decay. Black holes will evaporate through Hawking radiation. Eventually, nothing remains but a dilute gas of photons and leptons, spreading farther and farther apart in an ever-expanding void. The universe won't end with a bang. It'll end with eternal silence. But if dark energy strengthens over time, we face something far more violent: the Big Rip. In this scenario, the acceleration becomes so extreme that it overcomes not just gravity, but all the fundamental forces. Galaxies tear apart, then solar systems, then planets, then atoms themselves. The universe rips itself to shreds at the level of elementary particles. Current observations favor heat death over the Big Rip. But the recent DESI findings suggest dark energy might be more complex than we thought. We don't know enough yet to rule anything out definitively. What we do know is this: the voids are expanding. They're pressing against the cosmic web, and over immense spans of time, they're pulling the universe's large-scale structure apart. The beautiful foam-like pattern of filaments and walls surrounding vast empty regions won't last forever. It's already dissolving, slowly but inexorably, into isolated island universes drifting alone in an expanding sea of nothing. This story has landmarks. Vast cosmic structures so empty they defy comprehension. Places where the universe reveals what it's becoming. In 1981, astronomer Robert Kirshner was conducting a routine survey. He was mapping galaxies by measuring their redshift, trying to understand the large-scale structure of the universe. Standard work. Nothing unusual expected. Then he found something that shouldn't exist. A region of space roughly spherical in shape, centered about 700 million light-years from Earth. He expected to find around 2,000 galaxies in a volume that size. He found 60. The Boötes Void. Astronomers started calling it the Great Nothing. Its radius stretches 62 megaparsecs. That's nearly 200 million light-years across, one of the largest known voids in the observable universe. To put that scale into perspective, astronomer Greg Aldering calculated something unsettling. If the Milky Way had been located at the center of the Boötes Void, we wouldn't have discovered other galaxies existed until the 1960s. The nearest galaxies would have been so far away that even our most powerful telescopes of earlier eras couldn't have detected them. Think about that for a moment. Our entire understanding of cosmology, of the universe's structure and evolution, depends on being able to observe other galaxies. The Hubble expansion, dark matter, dark energy, all discovered by studying galaxies beyond our own. If we'd evolved in the Boötes Void, humanity would have spent millennia believing the Milky Way was the entire universe, a lonely island of stars in an infinite black ocean. We got lucky with our cosmic address, but the Boötes Void isn't unique. It's just one example of a phenomenon that appears throughout the universe. Astronomers have catalogued hundreds of voids, some smaller, some larger. The Eridanus Supervoid spans 1.8 billion light-years. It's associated with the cold spot in the cosmic microwave background, a mysterious region of space that appears colder than it should be, possibly because photons lose energy climbing out of such a massive underdensity. These structures challenge our understanding of cosmic evolution. According to the standard cosmological model, matter should be distributed relatively evenly throughout the universe on the largest scales. Small fluctuations, yes, but nothing that should create such enormous empty regions. Yet here they are, vast bubbles of near-nothingness, containing less than 1/10 the average density of matter in the universe. How did they form? The answer takes us back to the Big Bang itself. In the first moments after the universe began, quantum fluctuations created tiny variations in density. Some regions had slightly more matter, others slightly less. These differences were incredibly small, variations of just 1 part in 100,000. But gravity amplifies imbalances. Regions with more matter attracted even more matter. They grew denser. Regions with less matter lost what little they had to their denser neighbors. They became emptier. Over billions of years, this process created the cosmic web. Dense regions collapsed into galaxy clusters connected by filaments. Low-density regions expanded into voids. It's a natural consequence of how gravity sculpts space when you start with uneven initial conditions. But there's something else happening now. Something that changes the story. Dark energy. In dense regions, galaxy clusters, galactic filaments, gravity still dominates. Matter is packed closely enough that its gravitational attraction overcomes the expansion of space. Galaxies in these regions stay gravitationally bound. The expansion doesn't tear them apart. In voids, there's not enough matter for gravity to resist. Dark energy dominates completely. Space expands unimpeded, stretching the voids larger and larger. They grow faster than the cosmic average. They press outward against the surrounding cosmic web like inflating balloons. This means voids aren't passive features. They're active participants in cosmic evolution. They're engines of expansion, gradually pulling the universe's structure apart. And we might be living inside one. The KBC Void, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, is an immense underdensity, roughly 1 to 2 billion light-years across. Observations suggest the Milky Way sits near its center. We're in a region of significantly lower galaxy density than the cosmic average. This is a problem for cosmology. One of the biggest unsolved puzzles in modern physics is called the Hubble tension. When astronomers measure the universe's expansion rate using nearby supernovae and Cepheid variables, they get one answer: about 73 kilometers per second per megaparsec. When they measure it using the cosmic microwave background and large-scale structure data, they get a different answer: about 67 kilometers per second per megaparsec. That's a significant discrepancy, too large to be experimental error. Something fundamental is wrong with our understanding. Some researchers think the KBC void might explain it. If we're inside a supervoid, we experience a gravitational pull from the denser regions outside. This creates a peculiar velocity, motion that's separate from the Hubble expansion. Physicist Indranil Banik describes it like this: you can think of a supervoid as a homogeneous universe plus some concentrated negative mass. It has a repulsive gravitational effect. It raises the redshifts of galaxies beyond what cosmic expansion alone would produce. The theory method for measuring the Hubble constant averages expansion over the entire universe. The observational method only calculates it within the KBC Supervoid. If we're in a region where expansion appears faster than average, that explains why local measurements don't match global ones. The universe isn't expanding faster everywhere. It's just expanding faster here. This solution remains controversial. Not all cosmologists accept it. But it highlights something important. Voids aren't just empty. They're regions where the geometry of space-time itself differs from the cosmic average. They warp our measurements. They influence how we perceive the universe. And they're getting larger. Computer simulations of cosmic evolution paint a clear picture. As dark energy continues pushing space outward, voids expand. They stretch the filaments connecting galaxy clusters. Over time, those filaments thin and eventually break. The cosmic web fragments into isolated pieces. The timescale is immense. We're talking tens of billions of years. But the process is inevitable if dark energy remains constant or strengthens. In about 100 billion years, distant galaxies will recede so fast that their light can never reach us. The cosmic horizon shrinks. Future observers will see a much smaller, lonelier universe. Eventually, only the galaxies in our local gravitationally bound group remain visible. Everything else disappears beyond the expanding voids. But even that's temporary. Stars burn through their fuel and die. New stars can't form without fresh gas and dust. Galaxies go dark. Matter slowly decays. Black holes evaporate through Hawking radiation. The universe trends toward maximum entropy, a state where everything is evenly spread and nothing interesting can happen anymore. Heat death, the big freeze, an eternal cosmic winter, unless dark energy strengthens. The recent DESI findings suggest dark energy might be dynamic, evolving over time. If it's getting stronger, the expansion accelerates faster. Eventually, it overcomes not just gravity, but all the fundamental forces holding matter together. Galaxies tear apart first, then solar systems, then planets, then molecules, then atoms themselves. The universe rips itself to shreds at the level of elementary particles. This scenario, the Big Rip, is more violent than heat death. It's not a slow fade into darkness. It's a catastrophic unraveling of space-time itself. Current data favors heat death. The Big Rip requires phantom energy, a hypothetical form of dark energy, with properties most physicists consider implausible. But we don't know enough about dark energy to rule it out completely. What we do know is that voids are central to both scenarios. They're where dark energy does its work. They're the regions expanding fastest. They're already tearing the cosmic web apart, just very slowly. The beautiful foam-like structure of filaments and walls surrounding vast empty regions won't last. It's dissolving. The voids are winning. But here's what makes this truly unsettling. Voids aren't completely empty. They contain their own internal structure. Smaller voids within larger voids. Tiny filaments connecting the few galaxies that do exist inside. Even walls and clusters on smaller scales. It's a fractal pattern, self-similar across different size scales. Computer simulations reveal this hierarchical architecture. When you zoom in on a void, you find miniature versions of the cosmic web structure. When you zoom in on those features, you find even smaller substructures. The pattern repeats all the way down. This complexity makes voids fascinating laboratories for studying galaxy evolution. The 60 galaxies in the Boötes Void didn't form in typical environments. They evolved in near-total isolation. No mergers, no close gravitational interactions, no dense surroundings stripping away their gas. They're cosmic hermits. Studying them tells us what happens when galaxies develop alone. They tend to be smaller, bluer, and more gas-rich than galaxies in dense environments. They form stars more slowly. They retain their spiral structures longer because nothing disturbs them. In some ways, void galaxies represent a purer form of galaxy evolution. They show what happens when you remove all the complicating factors of crowded environments. They're test cases for theoretical models, but they're also reminders of how hostile voids are to structure formation. Out of the enormous volume of the Boötes Void, only 60 galaxies formed. The rest is just empty space, a testament to how thoroughly dark energy dominates these regions. And those voids are expanding into everything else. The cosmic web we observe today is a snapshot in time, a temporary configuration. Billions of years ago, the universe was denser, more uniform. The voids were smaller, the filaments thicker, galaxies closer together. Billions of years from now, the opposite will be true. Voids will dominate even more. Filaments will have thinned to nearly nothing. Galaxies will drift alone in expanding bubbles of emptiness. The universe is becoming less structured over time, more homogeneous, more void-dominated. It's a slow-motion dissolution of cosmic architecture. The voids are erasing the intricate patterns that gravity spent billions of years constructing. They're returning the universe to something closer to its initial state, uniform, featureless, empty. Except this time, there's no Big Bang to restart the process, no quantum fluctuations to seed new structure, just endless expansion, endless emptiness, endless silence. This is what voids represent, not just empty regions between galaxies, but the future of the universe itself. They're showing us where everything is headed. They're previews of cosmic heat death, scattered throughout space and time. When you look at images of the cosmic web, those beautiful maps showing filaments of galaxies surrounding vast dark regions, you're seeing a battle between gravity and dark energy. Gravity trying to pull matter together, dark energy trying to push space apart. For now, gravity holds its own in the densest regions, but it's losing ground. The voids are expanding. They're pressing against the filaments from all sides, and eventually, they'll win completely. The question isn't whether the voids will swallow the cosmic web. The question is how long it takes and what form the final expansion takes. Because the voids aren't just expanding into the structure around them, they're fundamentally changing what it means for structure to exist at all. The mechanics of how voids reshape space itself reveals something unsettling about the nature of expansion. When dark energy pushes space outward, it doesn't do so uniformly everywhere. Dense regions, galaxy clusters, filaments, massive walls of matter resist expansion through gravitational binding. Their internal gravity is strong enough to counteract dark energy's push. These structures stay coherent even as space expands around them. But voids have no such resistance. With less than 1/10 of the universe's average density, voids offer almost nothing for gravity to work with. Dark energy encounters minimal opposition. Space expands faster in voids than anywhere else, much faster. This differential expansion creates a feedback loop. As voids expand, they become even less dense. Lower density means weaker gravity. Weaker gravity means less resistance to expansion. Less resistance means faster expansion. Faster expansion means lower density. The cycle accelerates itself. Meanwhile, the surrounding cosmic web experiences mounting pressure from all directions. Imagine being squeezed between expanding bubbles. That's the situation for every filament, every wall, every cluster at the edges of voids. They're being compressed from multiple angles as voids press inward from all sides. Eventually, something has to give. The thinnest parts of filaments snap first. Galaxies at the edges drift away into expanding voids. The cosmic web develops gaps, Holes appear in what were once continuous structures. Over billions of years, the web fragments into increasingly isolated pieces. This process is already underway. We're witnessing it in real time through careful observations of galaxy distributions. Filaments are thinning, walls are stretching, the gaps between structures are widening measurably, and we're part of this process, whether we realize it or not. The KBC void, the massive underdensity surrounding our local cosmic neighborhood, puts us in a peculiar situation. We're not in the deepest part of this void. We're near the edge, in a relatively dense region called the local sheet. But the void extends for roughly 1 billion light-years around us. This location affects everything we measure about cosmic expansion. When astronomers observe distant galaxies to calculate the Hubble constant, the rate at which the universe expands, they're measuring expansion through the KBC void. But that's not representative of the universe as a whole. Expansion is faster inside voids than outside them. This creates what's called the Hubble tension. Two methods of measuring cosmic expansion yield different answers. Observations of nearby galaxies and supernovae give values around 72 to 75 kilometers per second per megaparsec. Measurements from the cosmic microwave background, light from the early universe, give values around 67 to 68. That's a significant discrepancy, not a rounding error. A genuine conflict that suggests either our measurements are wrong or our understanding of cosmic expansion is incomplete. Living inside a supervoid might explain this tension. Galaxies inside a void experience gravitational pull from the denser regions outside. This creates an effective outward force, a repulsive effect that makes local expansion appear faster than the cosmic average. From inside the void, the universe looks like it's expanding more rapidly than it actually is. Think of it as a perspective distortion. You're measuring expansion from inside a region where expansion is locally enhanced. Your measurements are accurate for your location, but don't reflect the global picture. Some cosmologists argue the KBC void can resolve the Hubble tension. Others remain skeptical. The debate continues. But the possibility that we're inside one of the universe's largest voids has profound implications beyond just measurement issues. It means our view of the cosmos is fundamentally shaped by emptiness. For most of human history, we assumed Earth occupied a special place. Then we learned we orbit an ordinary star in an ordinary galaxy in an ordinary part of the universe. The Copernican principle, the idea that we're not special, became a cornerstone of cosmology. But if we're inside a supervoid, that principle gets complicated. Voids aren't typical. They represent extreme underdensities. Less than 10% of the universe's volume consists of regions as empty as the KBC void. Being inside one isn't necessarily special in a meaningful sense, but it's statistically unlikely, and it affects what we can observe and how we interpret those observations. Civilizations in different cosmic environments would develop different cosmologies based on what they could see. A civilization in the Boötes Void would have faced extraordinary challenges discovering the broader universe. With only 60 galaxies in a region spanning 200 million light-years, their night sky would contain almost nothing beyond their own galaxy. No nearby galactic neighbors, no obvious evidence of a larger cosmic structure. Astronomer Greg Aldering calculated that if the Milky Way had formed in the center of the Boötes Void, we wouldn't have discovered other galaxies until the 1960s. Before that, Our most powerful telescopes wouldn't have been strong enough to detect the faint, distant galaxies at the void's edge. Our entire understanding of cosmology would have been delayed by decades or centuries. We might have developed completely different theories about the universe's structure. We might have assumed our galaxy was alone, that the universe consisted of a single island of stars surrounded by infinite emptiness. Only with mid-20th century technology would we have finally detected those distant pinpoints of light and realized the truth. This thought experiment highlights how profoundly our cosmic environment shapes our understanding. We're fortunate to live in a relatively dense region where galaxies are visible in abundance. Our view of the cosmic web is clearer than it would be from inside a void. But there's another, more disturbing implication. As voids continue expanding, future civilizations will face the same problem. Not because they're in voids like Boötes, but because expansion will have pushed everything so far apart that the universe effectively becomes a void from every perspective. Give it 100 billion years, maybe 200 billion. Distant galaxy clusters will have receded beyond the cosmic horizon, the boundary beyond which expansion carries objects away faster than light can travel. They'll disappear from view completely, not because they've been destroyed, but because space between us and them is expanding too rapidly for their light to ever reach us. Our descendants, if any exist, will look up at a much emptier sky. They'll see the local group, the Milky Way, Andromeda, and the few dozen dwarf galaxies gravitationally bound to them. Everything else will have vanished. No distant galaxies, no cosmic web, no evidence of the larger universe. And here's the truly unsettling part. They won't be able to discover cosmology the way we did. The evidence we use to piece together the Big Bang theory, the expansion of the universe, the cosmic microwave background, the abundance of light elements, all of that depends on observing distant objects. Without access to distant galaxies, future astronomers will have no way to measure cosmic expansion. They'll see a static universe containing only their local cluster. The cosmic microwave background will still exist, but it will have been redshifted to such long wavelengths that it becomes essentially undetectable. The faint afterglow of creation will fade into invisibility. Future scientists will look out and see nothing but their own galaxy cluster surrounded by permanent darkness. They might develop theories, they might speculate, but they won't have the observational evidence we have today. The universe will have hidden its own history through expansion. This raises an uncomfortable question. What evidence are we missing right now? If the universe has already expanded enough to push some structures beyond our cosmic horizon, we might be in the same situation as those future astronomers. We might be looking at an incomplete picture, unaware of what we can't see. There could be structures, patterns, or phenomena beyond our observational limits that would completely change our understanding of cosmology. We wouldn't know. We couldn't know. The information simply hasn't reached us yet, and never will. Voids guarantee that large portions of the universe remain forever unknowable. Every void represents a region where structure formation failed, where the initial density fluctuations were too small, where dark energy's influence overwhelmed gravity before significant clustering could occur. These regions tell us something important about the universe's initial conditions. The size and distribution of voids constrain models of cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang. Too many large voids would suggest different inflationary parameters. Too few would point in another direction. By mapping voids throughout the observable universe, cosmologists can test theories about the very earliest moments of cosmic history. But voids also tell us about the future. The Eridanus Supervoid offers a particularly striking example. This cigar-shaped void stretches 1.8 billion light-years across, making it one of the largest known structures. Its center sits 2 billion light-years away in the direction of the constellation Eridanus. What makes this void especially interesting is its connection to the CMB cold spot. The cosmic microwave background should be nearly uniform. Tiny temperature fluctuations exist, the seeds of cosmic structure, but they're small. Most variations are around 18 microkelvins. The cold spot is different. At its most extreme, the cold spot measures 140 microkelvins, colder than the average CMB temperature. That's nearly 8 times the typical variation. It's an anomaly that shouldn't exist according to standard cosmological models, unless it's caused by a supervoid. When CMB photons travel through a void, they experience a subtle energy loss. The void's expansion stretches space as photons cross it, slightly redshifting their wavelengths. This redshift appears as a temperature decrease when we measure the CMB. The Eridanus Supervoid sits precisely in the direction of the cold spot. Its size and distance match what would be needed to create the observed temperature anomaly. The correlation is strong enough that most cosmologists now accept the connection. But here's what's disturbing about this. The Eridanus Supervoid is so massive that it noticeably affects the cosmic microwave background. This isn't a small perturbation. This is a structure so dominant in its region of space that it leaves an imprint on the universe's oldest light. The void's gravitational influence, or rather its lack thereof, shaped space-time enough to create a detectable signal in radiation that has been traveling for nearly 14 billion years. That reveals the true scale of void's influence. They're not passive features. They're active participants in cosmic evolution. They shape the flow of matter, the propagation of light, the curvature of space-time itself, and they're growing larger and more influential with every passing moment. The question isn't whether voids will dominate the universe's structure. They already do. They occupy more volume than all the filaments, walls, and clusters combined. The question is, what happens as they continue expanding and merging? Small voids grow. Large voids become supervoids. Supervoids merge into even larger structures. The hierarchy continues upward indefinitely as long as dark energy keeps driving expansion. Eventually, you reach a point where the distinctions become meaningless. When voids dominate so thoroughly that the cosmic web has fragmented into isolated islands, the universe becomes effectively homogeneous again. Not because matter is evenly distributed, but because the distances between structures are so vast that local variations don't matter on cosmic scales. It's a strange inversion. The universe starts nearly homogeneous after the Big Bang. Structure formation breaks that homogeneity. Gravity creates the cosmic web. But dark energy, working through voids, gradually erases those structures and returns the universe to large-scale uniformity. Except this time, the uniformity is one of emptiness rather than density. The cosmic web we observe today sits at a special moment in universal history. Early enough that structure still exists, late enough that we can observe it. This window won't remain open forever. In a few billion years, astronomers living in the Milky Way We'll look out at the night sky and see something fundamentally different from what we observe today. They'll still see stars. The Milky Way itself will remain, likely merged with Andromeda by then. Our local group of galaxies will persist as a gravitationally bound structure. But beyond that, darkness. The cosmic web will have faded from view. The distant galaxies we photograph today, those beautiful spiral and elliptical galaxies scattered across deep field images, will have receded beyond the cosmic horizon. The expansion of space will have carried them away faster than light can travel. Not because they're moving through space faster than light, but because space itself is expanding between us and them. This isn't speculation. The mathematics is straightforward. We can calculate exactly when different structures will disappear from our observable universe. The most distant galaxies we currently observe are already on the edge. Their light has been traveling for over 13 billion years to reach us. But they're not 13 billion light years away. Due to cosmic expansion, they're now more than 30 billion light years distant. Every year, more galaxies cross the threshold where their light will never reach us. Within about 100 billion years, every galaxy beyond our local gravitationally bound cluster will have vanished from view. Future astronomers won't be able to observe them no matter how powerful their telescopes become. The light simply won't arrive. Those galaxies will still exist, presumably. But they'll be causally disconnected from us, separated by expanding voids that space itself has stretched beyond any possible contact. That's when the real isolation begins. Imagine being an astronomer in that far future. You'd have incredible technology, telescopes that dwarf anything we possess, computational power we can't conceive. But when you point your instruments at the sky beyond your local cluster, you'd see nothing. No distant galaxies, no quasars, no cosmic microwave background radiation to study. You'd have no way to discover the Big Bang, no evidence for cosmic expansion, no ability to measure the universe's age or composition. Your entire understanding of cosmology would be limited to your local island of matter, floating in an ocean of expanding emptiness. Would you even realize your universe was larger than what you could observe? Probably not. You'd have no reason to suspect it. Your observable universe would appear to be just your local cluster, surrounded by infinite darkness. You'd likely conclude that the universe is static, eternal, and small. All the cosmological knowledge we've gained over the past century would be inaccessible to you. Not because you lack intelligence or curiosity, but because the evidence has literally moved beyond reach. This raises an uncomfortable question. What knowledge is already beyond our reach? We can only observe the universe within our current cosmic horizon. Light from beyond that boundary hasn't had time to reach us yet. But as the universe expands, that horizon isn't growing to encompass more space. It's shrinking in terms of what we'll ever be able to observe. There could be structures, phenomena, entire categories of cosmic objects that exist beyond what we can currently see. And if they're in regions that are expanding away from us faster than light, we'll never detect them. Ever. The voids are central to this process. They're not passive bystanders. They're the mechanism through which cosmic isolation occurs. As voids expand, they push everything apart. The filaments stretching between them grow longer and thinner. Galaxy clusters become more isolated. The cosmic web transitions from an interconnected network to scattered islands. This process accelerates over time. Dark energy density remains constant per unit volume, But as the universe expands, the total volume of space increases. More volume means more dark energy. More dark energy means faster expansion. Faster expansion means voids grow larger. It's a runaway process with no natural stopping point. Right now, we're living in what might be the optimal epoch for observational cosmology. Early enough that the cosmic web still exists. Late enough that we've developed the technology to observe it. This window is temporary. Our descendants billions of years from now will have access to less cosmological information than we do, not more. The universe won't have changed its fundamental nature, but the observable portion will have shrunk dramatically unless we preserve that knowledge. Unless we record everything we discover about the distant universe, about cosmic expansion, about the structures that exist beyond our local cluster. Because eventually, there will be no way to verify these observations independently. Future civilizations will have to take our word for it, or they'll dismiss it as mythology. Ancient stories about a time when the sky was filled with countless galaxies, when light from the beginning of time could be detected, when the universe was young and full of structure. Without evidence, how would they distinguish scientific observation from creative fiction? This is already happening on smaller scales. There are galaxies that were visible to us 1 billion years ago that have now receded beyond observation. We could have photographed them then, if we had possessed the technology, but we didn't. And now they're gone from our view permanently. What did we miss? What structures existed in the observable universe 1 billion years ago, 5 billion years ago, 10 billion years ago, that we can no longer see because they've been carried beyond the cosmic horizon? We'll never know. That information is lost, not destroyed, but inaccessible, which amounts to the same thing from our perspective. The voids don't just separate us spatially, they separate us temporally. They cut us off from information about the universe's past and future. Consider the cosmic microwave background. Right now, we can detect it clearly. It provides our most detailed information about the early universe. But the CMB is redshifting as the universe expands. Its wavelength is being stretched to longer and longer values. Eventually, it will redshift into radio wavelengths so long they become impossible to detect against background noise. The CMB will fade from observability. When that happens, future astronomers will lose access to direct observations of the universe when it was 380,000 years old. They'll have to rely on theoretical models and historical records. No independent verification will be possible. The same applies to distant galaxies. We can currently observe galaxies as they appeared billions of years ago. Their light carries information about cosmic history, about how galaxies formed and evolved, about the expansion rate at different epochs. As those galaxies recede beyond the horizon, that information vanishes. We lose our window into those periods of cosmic history. The universe is becoming observationally simpler over time, more homogeneous, less structured. Not because structure is disappearing, but because we're losing the ability to see it. In the far future, the observable universe will appear almost perfectly uniform, a single cluster of galaxies surrounded by darkness. No evidence of larger-scale structure, no visible cosmic evolution, just static isolation. That's the long-term consequence of expanding voids. Not just physical separation, but informational isolation. The universe fragments into causally disconnected regions, each unable to communicate with or observe the others. We're watching this process unfold in real time. Every year, roughly 20,000 galaxies cross beyond our cosmic event horizon. They're still out there, presumably, but their light will never reach us. They've become part of a universe we can know exists, but cannot observe. This isn't some distant future concern. It's happening now. The universe we can observe is smaller today than it was yesterday, and it will be smaller tomorrow than it is today. The window is closing, not quickly by human standards, but cosmically speaking, we're in the final moments of a brief era when the universe is both large enough to contain magnificent structure and young enough that we can still observe it. What are we doing with this opportunity? We're mapping the cosmic web in unprecedented detail. Surveys like DESI are cataloguing millions of galaxies, measuring their positions and velocities, reconstructing the large-scale structure of the universe. That data will remain valuable long after the structures themselves have receded from view. We're studying the cosmic microwave background with ever-increasing precision, extracting every bit of information we can about the early universe before that signal fades beyond detection. We're observing distant galaxies and quasars, looking back in time to witness cosmic history as it actually unfolded, building a record that future generations will be unable to verify but might still find useful. Because once the voids have expanded sufficiently, once the cosmic web has fragmented into isolated islands, once the observable universe has shrunk to just our local cluster, there will be no second chances, no way to recover that lost information. The universe won't care. It will continue expanding regardless of whether anyone is observing it. Voids will keep growing. Dark energy will keep pushing. The cosmic web will keep fragmenting. But for conscious beings trying to understand the cosmos, this represents an irreversible loss, a closing door that will never reopen. You might wonder whether this matters. After all, we're talking about timescales of billions of years. Humanity will likely be unrecognizable by then, if it exists at all. But the principle matters. The universe is not infinitely knowable. There are limits to what can be observed, not because of technological constraints, but because of the fundamental structure of space-time. Information is being lost constantly, not destroyed, but moved beyond reach. The expanding voids ensure this. They're not just empty regions of space. They're information barriers, causality boundaries, horizon generators, and they're winning. Slowly, inexorably, they're separating everything from everything else, breaking connections, severing information flows, fragmenting the universe into isolated pockets. The cosmic web we observe today is temporary, a fleeting pattern that emerged from the Big Bang's quantum fluctuations, grew under gravity's influence, and is now being dismantled by dark energy's relentless push. We're living in the middle of that story, after the formation, before the dissolution, in the brief window when structure exists and can be observed. That makes our era special, not because the universe treats us differently, but because we happen to exist at a time when cosmological observation is possible on the largest scales. Future civilizations won't have that privilege. They'll inherit a darker, emptier, more isolated cosmos, one where the evidence for the universe's grand structure has receded beyond the horizon, carried away by the same expanding voids that shaped that structure in the first place. The voids give, and the voids take away. They created the space for cosmic structure to form. Now they're erasing it from view, one galaxy at a time. But there's another angle to this cosmic isolation that we haven't considered yet. One that makes the situation considerably more unsettling. The voids aren't just passively expanding, they're actively changing the rules of physics in their regions of influence. This sounds like science fiction, but it's a direct consequence of general relativity. Space-time isn't a static background where events happen. It's dynamic, responsive to the presence or absence of mass and energy. Where there's matter, space-time curves. Where there's emptiness, it behaves differently. Inside a massive void, the local geometry of space-time shifts. Slightly, subtly, but measurably. Galaxies inside voids experience gravitational effects from the surrounding cosmic web pulling outward on them. This creates what physicists call a gravitational potential well, but inverted. Instead of falling into a region of high density, matter inside a void is being pulled toward the edges. The result? The expansion rate inside voids differs from the expansion rate in denser regions, not by much. We're talking about differences that require extraordinarily precise measurements to detect. But those differences compound over cosmic timescales and distances. This creates a problem, a significant one. When we measure the Hubble constant, the number that tells us how fast the universe is expanding, we get different answers depending on how we measure it. Observations of distant supernovae give one value. The cosmic microwave background gives another. These measurements should agree. They don't. This discrepancy is called the Hubble tension, and it's one of the biggest unsolved problems in modern cosmology. What if the tension isn't caused by measurement error or new physics? What if it's because we're sitting inside a void? The KBC Supervoid, named after the astronomers who studied it, is roughly 1 to 2 billion light-years in diameter. Observations suggest the Milky Way lies somewhere near its center. This isn't a small feature. It's one of the largest underdensities in the observable universe. If we're inside such a structure, our local measurements of cosmic expansion would be skewed. The void acts like a lens, distorting our view of the universe beyond it. Galaxies inside experience a different expansion rate than the cosmic average. Think of it as living in a valley and trying to measure the height of the surrounding mountains. Your perspective is fundamentally biased by your location. You're not seeing the landscape from a neutral vantage point. Some researchers propose this explains the Hubble tension entirely. The supernovae we observe are mostly within or near the KBC Supervoid, giving us a local measurement. The cosmic microwave background samples the entire universe, giving us the global average. Different regions, different expansion rates, different numbers. This would be convenient. It would resolve a major cosmological crisis without requiring new physics or exotic explanations. But it creates a philosophical problem that's arguably worse than the measurement discrepancy. If our location inside a void significantly affects our observations, then we're not seeing a representative sample of the universe. Our measurements are biased by cosmic geography. The laws of physics we derive from local observations might not accurately describe the cosmos as a whole. This undermines a fundamental assumption in cosmology, the cosmological principle. The idea that the universe looks roughly the same everywhere if you zoom out far enough. That there's no special location, no privileged perspective. Living inside one of the largest voids in the observable universe suggests we might occupy a rather unusual location after all. Not special in any meaningful sense. The void didn't form because we're here. We're not at the center by design. Pure coincidence places us in this particular region of space-time. But coincidence or not, our location matters. It affects what we can observe and how we interpret those observations. Consider the implications. If the KBC Supervoid significantly influences our measurements, then our entire cosmological model might need adjustment. The parameters we've carefully calibrated, the confidence we've built in our understanding of dark energy and cosmic expansion, all potentially compromised by location bias. We can try to correct for this, account for our position inside a void when analyzing data, adjust our models to compensate for local effects. But that assumes we know the void's exact size, shape, and density profile. We don't. Not precisely. Mapping the three-dimensional structure of cosmic voids requires extensive observation and complex analysis. Current surveys are working on this, but we're still refining the details. Meanwhile, dark energy continues its work. The KBC Supervoid continues expanding. The cosmic web continues fragmenting. And we're left wondering whether our measurements reflect universal truths or local circumstances. This uncertainty extends beyond just the Hubble constant. Any observation that depends on distance measurements or expansion rates could be affected. The age of the universe, the density of dark energy, the timeline of cosmic structure formation. Not catastrophically wrong. The corrections wouldn't be enormous, but significant enough to matter when we're trying to understand the universe's fundamental nature with precision. There's also the Eridanus Supervoid to consider. Located about 2 billion light-years away, it's even larger than the KBC void, roughly 1.8 billion light-years across, one of the biggest structures ever detected. This void has its own peculiar signature. It's associated with the CMB cold spot, an anomalously cold region in the cosmic microwave background. The spot is about 70 microkelvins colder than average. Doesn't sound like much, but in the incredibly uniform CMB, it stands out dramatically. At some points, the cold spot is 140 microkelvins below average. That's far colder than random fluctuations should produce. The Eridanus Supervoid might explain this. As CMB photons pass through such a massive underdensity, they lose energy climbing out of the gravitational potential. This creates a cold spot in the background radiation. Except the math doesn't quite work. The void isn't quite massive enough to produce the observed temperature deficit. Not by conventional physics anyway. So we're left with options. Either there's something unusual about the Eridanus Supervoid that we don't understand, or the cold spot has a different explanation entirely, or our understanding of how voids affect the CMB needs refinement. Each possibility opens new questions. Each suggests gaps in our cosmic comprehension. These aren't small voids. They're not local anomalies we can easily dismiss. They're fundamental features of large-scale structure, and they're challenging our ability to interpret observations accurately. The problem compounds when you consider that we can only observe voids in detail out to a certain distance. Beyond that, they become difficult to map precisely. We can infer their presence from how they affect visible structures, but direct measurement becomes increasingly uncertain. This means our catalogue of cosmic voids is incomplete. We know they exist throughout the observable universe. We know they dominate the volume of space. But we can't map everyone, can't measure every effect, can't fully account for how they influence our observations. It's like trying to understand ocean currents while only being able to sample a few scattered locations. You can build a model, make predictions, test hypotheses. But you're always aware that your data is incomplete, your perspective limited. Voids represent the majority of cosmic volume, but contain almost none of the matter. This creates a strange inversion in astronomy. We spend most of our time studying the rare, dense regions where galaxies cluster, because that's where the light is. That's what we can observe directly. The voids remain mysterious, not for lack of interest, but because emptiness is hard to study. You can't point a telescope at nothing and expect to learn much. Instead, we observe the boundaries, map the edges where voids meet filaments, study the few galaxies that exist in void interiors. Watch how light from distant sources bends as it passes through these underdense regions. From these indirect observations, we reconstruct void properties, infer their shapes, their expansion rates, their effects on cosmic evolution. But there's always uncertainty, always the possibility that we're missing something important because we're observing from inside the structure we're trying to understand. This is the fundamental challenge of cosmology. We have one vantage point, one moment in cosmic history, one set of observable phenomena. From this limited perspective, we're attempting to understand the entire universe across all of space and time. Voids make this harder. They introduce spatial variation in cosmic properties. They create regions where expansion behaves differently. They affect light propagation in ways we're still working to fully understand. And they're winning, slowly separating everything, creating more and more isolated pockets where future observers will have even less information to work with than we do. You might think technology will save us. Better telescopes, more sensitive detectors, more sophisticated analysis techniques. Surely we can overcome these limitations with sufficient ingenuity. But there are hard limits. Light speed is absolute. The cosmic horizon is real. Information beyond certain distances is permanently inaccessible, not because our instruments are inadequate, but because the universe's structure prevents that information from ever reaching us. Voids enforce these limits. Their expansion pushes regions of space beyond our observable reach. The information those regions contain, the galaxies they host, the structures they form, all lost to observation. Not destroyed, but separated from us by expanding space. This is already happening, has been happening for billions of years, will continue happening for billions more. Every second, some region of space crosses the threshold from observable to forever hidden. The cosmic horizon shrinks. The observable universe becomes smaller in terms of what we can causally access, even as space itself continues expanding. Voids drive this process. In dense regions, matter's gravity partially counteracts cosmic expansion. Structures can remain gravitationally bound, even as space expands around them. But voids have no such anchor. Nothing holds them together. Dark energy pushes unopposed, stretching space faster and faster. The question becomes, how much of the universe have we already lost? How many galaxies have receded beyond the cosmic horizon? How much structure has expanded away from us faster than light can travel? We can calculate this. The math is straightforward. The results are sobering. Most of the universe is already beyond our reach. The observable universe represents a tiny fraction of the total cosmos. Everything beyond about 46 billion light-years is causally disconnected from us. We will never receive signals from those regions, never observe what happens there, never confirm whether the same physical laws apply. Voids occupy most of that invisible volume. Vast empty regions we can never map, never study, never understand in detail. And the boundary keeps moving, keeps shrinking, keeps cutting us off from more and more of cosmic reality. This isn't speculation. This is direct consequence of measured expansion rates and well-established physics. The universe we can observe is temporary. The information we can access is finite. The window for cosmic archaeology is closing, not quickly, not on human timescales, but inevitably. Future civilizations, if they exist, will inherit a darker cosmos, fewer visible galaxies, less accessible information, a smaller observable universe despite living in the same expanding space we inhabit now. They'll have to trust our records, our measurements, our observations made during this brief era when the cosmic web was still visible and the universe's large-scale structure could still be mapped. Assuming those records survive, assuming future beings can interpret them correctly, assuming the information doesn't get lost in the vast stretches of time between now and then. Voids guarantee this future. Their expansion is inexorable. Dark energy shows no signs of weakening. The cosmic web will fragment. The observable universe will shrink. Information will be lost. We're documenting what we can while we can. Building catalogues of galaxies, mapping voids, measuring expansion rates, recording everything before it disappears beyond the horizon. But we know we're in a race we can't win. The universe is larger than our ability to observe it. Voids are expanding faster than we can map them. Cosmic structure is fragmenting faster than we can document it. All we can do is observe, measure, record, and hope that what we learn now remains useful later, when direct confirmation becomes impossible. Yet within these vast empty regions exists something stranger than absence itself. Galaxies in voids aren't like galaxies elsewhere. They've evolved differently, aged differently, developed characteristics that challenge our understanding of how galaxies form. These void galaxies live in isolation, no neighbors for millions of light years, no gravitational interactions pulling at their structures, no mergers disrupting their evolution, just slow, solitary existence in the emptiness between filaments. The Boötes Void contains about 60 such galaxies, scattered across its 200 million light-year radius like forgotten islands in an ocean of space. Each one represents a puzzle astronomers are still trying to solve. Why do they exist at all? Standard galaxy formation theory suggests galaxies need density, material to collapse, gravitational wells deep enough to pull gas and dark matter together. Voids lack these conditions. They're defined by their absence of mass. Yet void galaxies persist. They tend to be smaller than average, bluer in color, indicating younger stellar populations, more gas-rich, suggesting active star formation, less evolved overall compared to galaxies in denser environments. This makes sense on one level. Isolated galaxies avoid the interactions that strip away gas and shut down star formation. They maintain steady, uninterrupted growth over cosmic time. But it raises another question. How did they form in the first place? Current theory suggests they condensed from slight overdensities in the early universe. Tiny fluctuations that managed to overcome void expansion and collapse into galaxies. Statistical outliers that beat the odds. Once formed, they continued evolving in their lonely environments. No harassment from neighbors, no tidal stripping, no ram pressure from hot intracluster gas. Just gradual, peaceful star formation fueled by pristine gas infall. These galaxies provide laboratories for studying galactic evolution in its purest form. No environmental effects complicating the picture, no interactions distorting their structures, just gravity, gas dynamics, and star formation operating without interference. Observations reveal fascinating details. Void galaxies rotate differently than their counterparts in dense regions. Their stellar populations show distinct age distributions. Their chemical compositions tell stories of isolated enrichment. Some contain unusually high proportions of dark matter. Their rotation curves suggest dark matter halos that extend far beyond visible stellar disks. This makes sense given their formation history in low-density regions where dark matter dominates. Others show signs of past activity, ancient bursts of star formation followed by long quiescent periods, suggesting their evolution proceeded in fits and starts rather than steady progression. The few galaxies that exist in supervoids like Boötes represent extreme cases. They've spent billions of years in regions where cosmic expansion dominates completely, where even the small gravitational influences present in typical voids barely exist. These galaxies challenge our understanding of minimum conditions for galaxy formation. They demonstrate that galaxies can form and persist even in the most hostile environments imaginable for structure formation. But their isolation makes them difficult to study. Distance presents obvious challenges. Low luminosity compounds the problem. Many void galaxies remain too faint for detailed spectroscopy with current instruments. What we have learned suggests they're windows into cosmic history, preserved examples of galaxy evolution without environmental influence, natural experiments showing what happens when gravity alone shapes galactic destiny. Their existence also highlights something profound about void structure. Voids aren't completely empty, not even supervoids. They contain gas, dark matter, radiation, just far less than elsewhere. This minimal matter content follows the large-scale structure laid down by initial quantum fluctuations. Even in voids, density variations exist. Smaller subvoids within larger voids, filamentary structures on reduced scales, a hierarchical pattern repeating across all size ranges. Simulations reveal this complexity. High-resolution models show voids containing internal structure, mini-walls, tiny filaments, regions of slight overdensity where void galaxies preferentially form. The cosmic web extends even into voids themselves, just at lower amplitude, fainter, more subtle, but present nonetheless. This hierarchical structure matters for understanding void expansion. It's not uniform empty space expanding uniformly. It's a complex environment where expansion rates vary depending on local density. In the very emptiest regions, expansion proceeds fastest. Dark energy dominates completely. Space stretches at maximum rate allowed by cosmic expansion. In slightly denser regions, matter provides small gravitational resistance, not enough to prevent expansion, just enough to slow it marginally compared to the emptiest areas. Over time, this differential expansion amplifies existing density contrasts. The emptiest regions become emptier. The slightly denser regions become relatively denser by comparison. Void structure evolves, changes, develops more pronounced internal features as expansion continues. This evolution affects the few galaxies living inside voids. As space expands around them, their isolation increases. Neighbors that were merely distant become unreachably far. The universe fragments on progressively smaller scales. Eventually, even void galaxies will lose sight of each other. Expansion will carry them beyond each other's cosmic horizons. They'll become isolated, not just spatially, but causally, forever alone in their expanding bubbles of space. This fate awaits all cosmic structure eventually, but void galaxies will experience it first. They're the vanguard of cosmic isolation. Preview of what awaits all galaxies given sufficient time. The timeline varies. Void galaxies in supervoids might lose contact with neighbors within tens of billions of years. Galaxies in denser regions could maintain visibility for hundreds of billions of years. But the outcome remains identical. Isolation, darkness, expanding emptiness between all structures. This brings us back to the fundamental nature of voids themselves. They're not aberrations, not unusual features that somehow formed despite cosmic uniformity. They're integral components of large-scale structure, necessary consequences of how gravity and expansion interact. The cosmic web requires voids. Matter concentrating in filaments must come from somewhere. That somewhere is voids. They're the source regions that supplied material to denser areas. During cosmic history's early phases, matter flowed out of low-density regions into high-density ones. Gravity pulled material toward overdensities. Expansion pushed matter away from underdensities. The combination created the foam-like structure we observe. Voids represent those underdensities grown to cosmic proportions. Regions where outflow exceeded inflow, where expansion overcame gravity, where emptiness won. This process continues today. Matter still flows out of voids toward filaments. The process has slowed as expansion accelerated, but it hasn't stopped. Voids still drain, still feed material to surrounding structures, still expand and empty themselves further. The difference now is dark energy's dominance. Early in cosmic history, matter density was higher, gravity stronger, expansion slower. Voids formed but grew gradually. Now, with dark energy driving accelerated expansion, voids grow faster. Their expansion rate increases over time. The drainage process accelerates. This acceleration has profound implications for future structure. The cosmic web we observe represents a temporary phase, a brief era when structure was visible before void expansion tears it apart. In the deep future, voids will dominate completely. They'll occupy most of space, most of volume, most of the universe's geography. Dense regions will exist as scattered islands, isolated galaxy clusters separated by vast expanding emptiness. Each cluster causally disconnected from all others. Within those islands, local physics continues. Stars form and die. Galaxies orbit each other. Gravity operates normally. But beyond the cluster boundaries, exponentially expanding void. From inside such a cluster, the universe would appear dramatically different than today. No distant galaxies visible. No cosmic web structure, no evidence of expansion beyond the local group. Observations would show only nearby galaxies bound by gravity. Everything else would have receded beyond the cosmic horizon, disappeared into expanding void. Astronomers in that era would face impossible challenges reconstructing cosmic history. No access to distant light, no ability to observe early universe, no evidence of the Big Bang beyond local thermal radiation. They'd have to trust ancient records, measurements made during the current era when observation was still possible, assuming those records survived billions of years of cosmic time. This scenario isn't speculation. It's the predictable outcome of measured expansion rates and well-established cosmology. The math is straightforward, the conclusions unavoidable. voids will consume the observable universe, not by destroying structures, by separating them beyond the distance light can travel, by expanding space faster than causality can propagate. The process has already begun. Already galaxies are receding beyond our cosmic horizon. Already information is being lost. Already the observable universe shrinks in terms of accessible content. We're living in a golden age of cosmology, an era when the universe's large-scale structure remains visible, when we can still observe the cosmic web, still map voids, still measure expansion across cosmic time. This window won't remain open. Current estimates suggest we have perhaps 100 billion years before distant galaxies fade from view, before void expansion carries them beyond observation. That sounds like plenty of time, and it is, by human standards. But it's brief on cosmic scales, a tiny fraction of the universe's total lifetime, a momentary window when comprehensive observation remains possible. After that window closes, voids will have effectively swallowed the universe, not through destruction, through separation. By expanding space until structures become causally isolated, the universe will still exist, galaxies will still shine, stars will still burn, but in isolation, each structure alone in its expanding bubble, unable to observe or influence anything beyond its local gravitational domain. This represents the ultimate triumph of void expansion, the final consequence of dark energy's dominance, the inevitable endpoint of accelerated cosmic expansion. Voids started as slight underdensities, statistical fluctuations in the early universe's matter distribution. They grew through gravitational drainage and cosmic expansion, evolved into the massive empty regions we observe today. And they'll continue growing, continue expanding, continue separating structures until isolation becomes complete. We can observe this process, measure it, calculate its progression, but we cannot stop it, cannot reverse it, cannot prevent the fragmentation it will cause. All we can do is document what we observe while observation remains possible. Map the cosmic web before it fragments. Measure void expansion before it carries everything beyond reach. Record the universe's large-scale structure before that structure becomes invisible. Because eventually, voids will hide everything. Conceal the universe's true scope behind horizons of expanding space. Transform the rich cosmic landscape into isolated islands separated by unbridgeable distances. The terrifying void isn't a single structure. It's the collective future of all voids, the eventual state toward which cosmic expansion drives us. A universe fractured by emptiness, separated by space expanding faster than light can cross it. That future becomes clearer as we examine what dark energy actually does. Dark energy doesn't behave like normal forces. It doesn't weaken with distance, doesn't diminish as space expands. Instead, it maintains constant density throughout space. As the universe grows, more space appears, and that new space carries the same dark energy density as the old space. Think about what this means. Normal matter gets diluted by expansion. Galaxies spread farther apart. Their gravitational influence on each other weakens, but dark energy grows stronger in total effect because there's more space for it to occupy. This is why voids expand so effectively. They're regions where dark energy dominates completely, where matter is too sparse to provide meaningful gravitational resistance. The expansion isn't fighting against anything substantial. It's just stretching space according to dark energy's inherent properties. we can measure this effect directly. Observations show the universe's expansion rate increasing over time, not slowing down as gravity would predict, accelerating, getting faster with each passing billion years. This acceleration started roughly 5 billion years ago. Before that, the universe's expansion was decelerating. Gravity was winning the cosmic tug-of-war. Matter density was high enough that gravitational attraction slowed expansion. But as expansion continued, matter spread thinner. Its gravitational influence weakened, and dark energy, maintaining constant density, eventually took over. The transition marked a fundamental shift in cosmic evolution. Since then, dark energy has driven everything, shaped the universe's fate, determined how structures evolve, and guaranteed that voids would eventually dominate the cosmic landscape. The mathematics are straightforward. Dark energy contributes roughly 68% of the universe's total mass energy content. Dark matter adds another 27%. Normal matter, everything we can see and touch, makes up just 5%. Those percentages tell a story. The universe is fundamentally made of things we don't understand. Dark energy and dark matter completely dominate. Ordinary matter is almost an afterthought in the cosmic budget. But here's what makes dark energy particularly strange. It behaves like Einstein's cosmological constant, a property of space itself rather than something in space. Every cubic meter of vacuum carries the same amount of dark energy, regardless of what else occupies that region. Einstein originally introduced the cosmological constant to keep the universe static. He thought gravity would cause collapse and added a repulsive term to balance it. When Hubble discovered cosmic expansion, Einstein called the constant his greatest blunder. Except it wasn't a blunder. It was prescient. The cosmological constant appears to be real. It's just not serving the purpose Einstein intended. Instead of preventing collapse, it's driving acceleration, pushing the universe toward eternal expansion. Recent observations from the Dark Energy Spectroscopic Instrument add another layer of complexity. DESI's data suggests dark energy might not be constant after all. Its strength may have changed over cosmic time. The measurements indicate dark energy was stronger in the past, had a parameter value below -1.4 billions of years ago. That value has gradually increased to around -0.8 today. If confirmed, this changes everything. It means dark energy isn't a simple cosmological constant. It's a dynamic field that evolves, something more complex than Einstein's original concept. This possibility terrifies cosmologists and excites them in equal measure. A constant dark energy leads to predictable expansion, eternal acceleration at a steady rate. But evolving dark energy introduces uncertainty about the universe's ultimate fate. If dark energy continues weakening, expansion might eventually slow, perhaps even reverse. The Big Crunch scenario becomes possible again, all matter eventually collapsing back together in a reversal of the Big Bang. Alternatively, if dark energy strengthens, expansion could accelerate beyond control. The Big Rip scenario, space expanding so rapidly it tears apart galaxies, stars, planets, eventually atoms themselves. Current data doesn't definitively favor either extreme, but it suggests dark energy's behavior is more subtle than we assumed, more interesting, and potentially more consequential for cosmic evolution. This uncertainty doesn't change void expansion's current trajectory. Dark energy is driving voids larger regardless of its precise nature. The process continues whether the force remains constant or evolves gradually. But it affects our understanding of timescales, how quickly voids will isolate structures, how long the cosmic web will remain observable when the universe transitions to its final state. The mechanism of void expansion itself remains clear. Dark energy creates negative pressure throughout space. This pressure pushes outward. In regions where matter provides gravitational resistance, the effect is subtle. But in voids, where resistance is minimal, expansion proceeds unimpeded. You can visualize this as stretching a rubber sheet. Dense regions are like weights placed on the sheet. They resist stretching locally, create dimples in the fabric. But between the weights, the sheet stretches freely. Voids are those regions between weights, where space expands most efficiently, where dark energy's influence manifests most directly. The expansion doesn't add matter to voids. It doesn't create new galaxies or fill empty regions. It simply increases the distance between whatever matter already exists, spreads structures farther apart, creates more emptiness between islands of mass. This process is irreversible under current physics. Once space expands beyond a certain point, no force can bring separated structures back together. Light from one can never reach the other. Gravitational influence becomes impossible. Causal connection breaks permanently. We're watching this happen in real time, not dramatically. The changes occur over millions and billions of years, but they're happening, measurable, predictable based on known physics. Distant galaxies are already receding faster than light, not moving through space at superluminal speeds, which relativity forbids, but carried by space expansion. The space between us and them grows faster than photons can traverse it. These galaxies haven't disappeared yet. Light they emitted billions of years ago is still reaching us. We see them as they were when the universe was younger, when expansion hadn't yet carried them beyond the cosmic horizon. But eventually, that ancient light will be all we can receive. No new information will arrive. The galaxies will freeze in observational time, visible forever in principle, but showing only their ancient state. Then even that frozen image will fade, redshifted to longer and longer wavelengths, dimmer and dimmer, until it drops below any possible detection threshold. This is how voids consume the observable universe, not through destruction, but through separation. By expanding space until light can no longer bridge the distances involved. The process affects different structures at different rates. Galaxies within clusters remain gravitationally bound. Their mutual gravity overcomes local expansion. They stay together even as space stretches around them. But clusters themselves will eventually separate. The space between them will expand beyond gravitational influence. Each cluster will become isolated, an island universe alone in expanding void. Within those islands, galaxies might merge, collide and combine due to their orbital motions. Over trillions of years, each cluster could coalesce into a single massive galaxy, the last structure formation event before eternal isolation. That single galaxy would contain all the matter from its original cluster, billions of stars, vast reserves of gas and dust, black holes, nebulae, all the components of galactic structure, but nothing beyond. No neighboring galaxies, no cosmic web, just emptiness expanding forever in all directions. Beings living in such a galaxy would face profound observational limitations. Their entire observable universe would consist of one galaxy. Everything beyond would have receded past the cosmic horizon. They could study their own galaxy in detail, map its stars, understand local physics, but cosmology as we know it would be impossible. No way to observe the universe's large-scale structure. No evidence of the Big Bang beyond local thermal radiation. Their scientists would have to rely on theoretical models, ancient records if any survived, mathematical predictions rather than direct observation. A fundamentally different scientific enterprise than what we practice today. This scenario isn't science fiction. It's the predicted state of the universe in the distant future, based on measured expansion rates and well-established physical laws. The math is clear, the conclusions unavoidable. Some researchers have proposed this might already be affecting our observations. The KBC Void, a massive underdensity roughly 1 to 2 billion light-years across, may contain our galaxy near its center. If we're inside a supervoid, local expansion rates could differ from cosmic averages. This might explain the Hubble tension, the discrepancy between different methods of measuring the universe's expansion rate. Measurements using nearby supernovae yield values around 72 to 75 kilometers per second per megaparsec. But measurements from the cosmic microwave background give 67 to 68. The difference seems small, but it's statistically significant. A real problem for cosmology. Living inside a void could account for this. Galaxies within voids experience gravitational pull from denser regions outside. This affects their motion, creates apparent expansion rates that differ from the universal average. It's like measuring ocean currents from inside a whirlpool. The local motion doesn't represent the ocean's overall flow. You're in a special region where dynamics differ from the norm. This possibility highlights how voids affect everything, not just future cosmic evolution, but current observations. Our measurements, our understanding of fundamental cosmology. If we're in a void, we need to account for that in our models. Adjust our measurements. Recognize that local observations might not represent universal conditions. The implications extend beyond resolving measurement discrepancies. They affect our understanding of dark energy itself, how strongly it pushes, how it has evolved over time, what it predicts for the future. Voids serve as natural laboratories for studying dark energy. Regions where its effects dominate, where we can observe its influence without gravitational complications from dense matter. By mapping void expansion rates, we learn about dark energy's properties, how it behaves in different cosmic environments, whether its strength varies with location or time. These studies reveal patterns. Voids expand at predictable rates based on their size and the surrounding matter distribution. Larger voids grow faster. Isolated voids expand more efficiently than those adjacent to dense structures. The expansion follows mathematical relationships, power laws describing how void size increases with cosmic time. These relationships match predictions from dark energy models, confirming that we understand the basic physics. But puzzles remain. Why does dark energy have its observed strength? Why not stronger or weaker? The value seems arbitrary, yet it determines cosmic fate. If dark energy were slightly weaker, gravity would dominate. The universe would eventually collapse. If slightly stronger, expansion would have prevented structure formation. No galaxies, no stars, no planets. We exist in a narrow range where dark energy is strong enough to drive expansion, but weak enough to allow structure formation. This appears fine-tuned, suspiciously well-balanced. Some physicists invoke the anthropic principle. We observe these values because only universes with these properties produce observers. In other universes with different dark energy strengths, nobody exists to ask the question. Others suggest underlying physics we haven't discovered, mechanisms that set dark energy's strength based on fundamental principles, relationships between different forces that constrain possible values. The answer remains unknown. Dark energy is the universe's biggest mystery, more fundamental than dark matter, more consequential for cosmic evolution, and voids are where dark energy does its work most effectively, where we see its influence most clearly, where it shapes the universe's ultimate structure. As expansion continues, voids will dominate more completely, occupy larger fractions of space, press harder against remaining structures. The cosmic web will fragment, dissolve into isolated components separated by unbridgeable emptiness. This future is certain unless our understanding of physics is fundamentally wrong, unless dark energy behaves differently than observed, unless some unknown force intervenes. None of those possibilities seem likely. Dark energy's effects are too well measured, too consistent across different observation methods, too thoroughly integrated into cosmological models. We're watching the universe's transformation in progress, observing the early stages of void domination, documenting the cosmic web before it fragments beyond recognition. What makes this particularly urgent is the limited observation window. We have perhaps 100 billion years before distant structures fade from view. That sounds generous, but it's brief cosmically. After that window closes, comprehensive cosmology becomes impossible. Future observers will see only their local region, everything else hidden beyond horizons of expanding space. We're fortunate to live when observation remains possible, when the cosmic web stretches across our sky, when we can still map voids and measure their expansion. This era won't last, and once it ends, this knowledge becomes inaccessible to direct observation. The terrifying void isn't coming. It's already here, already expanding, already separating structures. The process has been underway for billions of years. We're just finally understanding what it means for the universe's future. Understanding this reality changes how we see our cosmic neighborhood. We're not passive observers watching from safe distance. We're participants in void expansion, part of the transformation happening throughout the universe. Our galaxy sits within the KBC Supervoid. This massive underdensity stretches across 2 billion light-years with us near its center. Living inside a void isn't immediately obvious. Stars still shine overhead. Nearby galaxies remain visible. But measurements reveal the truth. Galaxy density around us is significantly lower than cosmic average. About 30% less matter occupies our region compared to typical space. This deficit affects everything from cosmic expansion measurements to our understanding of dark energy's strength. The KBC void explains puzzling observations, why local expansion measurements differ from distant ones, why some cosmic parameters seem inconsistent across different methods. Our location inside this underdensity skews our perspective. Galaxies inside voids experience peculiar gravitational effects. The surrounding matter distribution pulls outward. This creates additional expansion beyond what dark energy alone produces. Local measurements therefore yield higher expansion rates than global averages. This resolves the Hubble tension partially. The discrepancy between local and distant expansion measurements makes sense when accounting for void location. We're measuring expansion from within an underdense region. Of course, our numbers differ from cosmic averages. But the KBC void raises uncomfortable questions about cosmological assumptions. Standard models assume uniform matter distribution, that we can measure universal properties from any location. Sitting inside a supervoid violates this assumption. How many other measurements are biased by our position? What cosmic truths remain hidden because we're observing from inside emptiness? These questions challenge fundamental cosmological principles. The Boötes Void offers even more dramatic perspective. This spherical emptiness contains only 60 galaxies across 200 million light-years. If our galaxy had formed there, human astronomy would have developed very differently. Imagine looking up and seeing almost nothing. A handful of faint smudges instead of thousands of galaxies. The cosmic microwave background, but little else beyond our galactic neighborhood. This would have been our reality from Boötes Void's center. We wouldn't have discovered the expanding universe until recently, couldn't have mapped large-scale structure, would have assumed our galaxy represented the entire cosmos for most of history. Only modern telescopes would have revealed the broader universe. This thought experiment reveals how location determines knowledge. Cosmic understanding depends on where you happen to form. Intelligence arising in void centers faces different observational challenges than we do. They would see emptiness as normal, the default cosmic state. Dense regions would seem exotic and unusual when finally discovered. Their cosmology would develop from fundamentally different starting assumptions. What makes voids truly terrifying isn't their current state. It's their relentless expansion. These regions grow continuously, consuming more space, pressing harder against remaining structures. The process never stops as long as dark energy dominates. Computer simulations project this future with disturbing clarity. Feed current observations into cosmological models. Let time advance. Watch what happens to the cosmic web over billions of years. Initially, the changes seem subtle. Voids expand gradually. Filaments thin slightly. The overall structure remains recognizable. But continue the simulation forward. The transformation accelerates. By 100 billion years from now, distant galaxy clusters will have receded beyond observation. Their light stretched to undetectable wavelengths. Space between us and them expanding faster than light can travel. They still exist, but become permanently invisible. Local structures survive longer. Our galaxy cluster remains gravitationally bound. Nearby groups stay visible. But the broader cosmic context disappears. Future observers will see only their immediate neighborhood. Everything else lost beyond unreachable horizons. Continue the simulation further, 1 trillion years forward. The Milky Way and Andromeda have long since merged, formed a single elliptical galaxy. Most stars have burned out. New formation has nearly ceased. The universe grows darker. Other galaxy clusters drift in isolation, separated by ever-expanding voids. No communication possible between them. Each island universe evolves independently, cut off from cosmic community by relentless expansion. Pushed to 100 trillion years, stars have exhausted available gas. No new stellar formation occurs anywhere. Existing stars gradually fade. White dwarfs cool. Neutron stars radiate away their heat. Black holes accumulate surrounding matter. The voids dominate completely, occupy 99.99% of space. Remaining matter concentrates in tiny pockets, islands of structure in an ocean of emptiness. The cosmic web has dissolved entirely. Only isolated remnants persist. At this point, void expansion becomes the universe's defining characteristic. Structure formation belongs to ancient history. The cosmos enters an era of dissolution. Remaining matter gradually disperses. Energy spreads thinner across expanding space. Eventually, even black holes evaporate through Hawking radiation. This takes incomprehensible timescales, 10 to the 100 years, numbers that dwarf cosmic age by factors beyond comprehension. But given infinite time, even this occurs. After black hole evaporation, essentially nothing remains. A few scattered particles. Photons stretch to wavelengths larger than galaxies. Space expanding ever faster. Temperature approaching absolute zero. This is heat death, the universe's final state under current physics. Some physicists propose alternatives. Maybe dark energy will weaken. Expansion could slow or reverse. The universe might collapse in a big crunch, resetting conditions for another cosmic cycle. Or dark energy might strengthen, becoming phantom energy that increases with expansion. This leads to the Big Rip scenario, where acceleration becomes so extreme it tears apart all structures, galaxies, stars, planets, eventually atoms themselves. Space-time ripped to shreds. Current evidence suggests neither extreme seems likely. Dark energy appears constant, the cosmological constant Einstein proposed. This points toward heat death as the most probable outcome. Recent observations add intriguing complexity. The dark energy spectroscopic instrument detects hints that dark energy may vary with time, possibly stronger in the past than now. If confirmed, this changes everything about long-term predictions. Evolving dark energy opens new possibilities. Maybe it will decay eventually, allowing gravity to reassert dominance. Structure formation could resume after a lengthy dormant period. The universe might prove more dynamic than current models suggest. These remain speculative possibilities. Current observations favor constant dark energy, heat death through endless void expansion. But cosmology has surprised us repeatedly. What seems certain often proves incomplete. What we know for sure is that voids expand now. This process continues unless something dramatic changes. The cosmic web faces inevitable dissolution on timescales we can calculate. This isn't speculation, it's observable physics projected forward. Living during the observable era feels fortunate. We can see the cosmic web intact, map large-scale structure, measure void expansion, understand how dark energy operates. Future observers won't have this opportunity. In 100 billion years, comprehensive cosmology becomes impossible. Too much universe has receded beyond observation. The cosmic microwave background will have redshifted beyond detection. Distant structures disappeared behind horizons. Only local measurements remain possible. This creates a knowledge extinction event. Information about cosmic history becomes permanently inaccessible. Future civilizations will face fundamental limits on what they can discover about their universe's origins and structure. We exist in a brief window, perhaps 200 billion years total, when universe-scale cosmology remains feasible. Before this window, stars hadn't formed yet. After it closes, observation becomes too limited. We're living in cosmology's golden age. This perspective makes current astronomical research more urgent. We're documenting the universe while documentation remains possible. Recording the cosmic web before it fragments. Measuring void expansion while voids still have defined boundaries. Every observation contributes to this comprehensive record. Galaxy surveys mapping large-scale structure, void catalogues documenting emptiness, expansion measurements tracking dark energy's effects. Together, these create a snapshot of the universe during its structured era. The terrifying aspect isn't void emptiness itself. Empty space seems peaceful, quiet. The terror comes from irreversibility. This process cannot stop under known physics, cannot reverse, cannot be prevented. We're watching the universe's transformation from complexity to simplicity, from structure to emptiness, from connection to isolation. And this transformation is guaranteed unless our understanding of fundamental physics is wrong. Even calling it terrifying might be projection. The universe doesn't care about our aesthetic preferences. Voids expanding is simply physics operating as it must. Dark energy doing what dark energy does. The cosmos following its natural trajectory. Perhaps terror comes from recognizing impermanence. The cosmic web we observe today is temporary. Like everything else in the universe, it formed from simpler initial conditions. It will dissolve into simpler final states. We're witnessing the middle chapter. The expanding voids teach us that structure is transient, emptiness is permanent. Given enough time, separation wins over connection. Dispersal overcomes concentration. The universe trends toward maximum entropy, toward heat death. But even this might not be the end. Quantum fluctuations could eventually create new structures. Given literally infinite time, new Big Bangs might emerge from quantum vacuum, resetting the cycle. These possibilities extend beyond current physics, into speculation about what might happen on timescales that make cosmic age seem instantaneous. We simply don't know if the universe has tricks we haven't imagined. What we can say is this: voids are expanding, the cosmic web is fragmenting, structure formation era is ending. We're living through a cosmic transition, from the universe's middle age toward its long decline. The process is measurable, inevitable, already underway. The void isn't coming to swallow the universe. It's already here, growing steadily, claiming more space with each passing moment, separating galaxies that will never reconnect, creating the isolation that defines the universe's far future. And we're watching it happen, recording the transformation, understanding the physics, documenting the cosmic web while it still exists as an integrated whole. This makes us witnesses to one of the universe's most significant transitions, from structure to void, from connection to isolation, from complexity to simplicity. The terrifying void is the universe's destiny. We are living in a universe that is forgetting itself. Every second, roughly 20,000 galaxies cross beyond the cosmic horizon. They're still out there somewhere, still burning through their fuel, still hosting whatever structures or systems, or perhaps even civilizations they contain. But their light will never reach us again. The space between us expands faster than photons can travel. These galaxies have become part of a universe we can know exists, but cannot observe. This isn't some distant future catastrophe. It's happening right now. While you've been reading this, while you've been breathing and thinking and existing, the observable universe has become measurably smaller in terms of what we can access, what we can study, what we can ever hope to understand. The voids are winning, not through any malicious intent, not through conscious effort, simply through the relentless mathematics of expansion. dark energy pushing space outward at an accelerating rate, creating more emptiness, more separation, more isolation. In 100 billion years, give or take, the cosmic web will have dissolved from view. Future observers will look up and see only their local galaxy cluster. Everything else will have receded beyond the horizon. The universe will appear smaller, darker, lonelier. Not because it has become smaller, but because observation has become impossible. Those future astronomers won't be able to discover the Big Bang, won't have access to the cosmic microwave background, won't be able to measure universal expansion. All the evidence we use to build modern cosmology will have literally moved beyond reach. They'll have to trust records, measurements made during our era when observation was still possible, assuming those records survive the immense stretches of time between now and then, assuming they can be interpreted correctly, assuming they're not dismissed as mythology. This is what voids do. They don't destroy information. They separate it, place it beyond reach, create permanent boundaries that even light cannot cross. We exist in a privileged moment. The universe is old enough that we've developed the technology to observe its large-scale structure, young enough that structure still exists to observe. This window is temporary, brief on cosmic scales, and it's closing. Every observation we make now carries added weight. Every measurement contributes to a record that future civilizations might never be able to verify independently. We're documenting the universe during its observable era, recording what exists before it disappears behind horizons we cannot penetrate. The Boötes Void contains 60 galaxies across 200 million light-years. The Eridanus Supervoid stretches 1.8 billion light-years. The KBC Void surrounds us with reduced density across 2 billion light-years. These aren't anomalies. They're the dominant features of cosmic structure. They occupy more volume than all the filaments and clusters combined, and they're growing, pressing against the cosmic web from all directions, stretching space faster in their interiors than in denser regions, creating differential expansion that will eventually fragment all large-scale structure into isolated pieces. The mathematics are clear, the physics well established, the outcome inevitable unless something dramatic changes in our understanding of fundamental forces. Dark energy dominates the cosmic budget. 68% of everything that exists. It doesn't dilute with expansion, maintains constant density as space grows. This means total dark energy increases as the universe expands. More space equals more push equals faster expansion. Faster expansion creates more space. The cycle accelerates itself. Voids provide the environment where this process operates most efficiently, where matter's gravitational resistance is minimal, where dark energy can stretch space unimpeded, where the universe's future is already visible. Looking at a void isn't just seeing emptiness, it's seeing what awaits all of space eventually, the final state toward which expansion drives everything, maximum entropy, heat death, eternal isolation in ever-expanding darkness. Some might find this depressing, the inevitable dissolution of all structure, the fragmentation of the cosmic web, the loss of observable universe, the approach of heat death. But perhaps there's something else worth considering. We are here, now, during the observable era, able to see the cosmic web intact, able to map voids and measure their expansion, able to understand what's happening and why. We are the universe becoming aware of its own transformation. Conscious matter capable of observing cosmic evolution. temporary arrangements of atoms that can contemplate their origins and fate. The voids are expanding. The cosmic web is dissolving. Structure formation is ending. These are facts we cannot change, but we can observe, measure, understand, record. Pass forward the knowledge we gain during this brief window when comprehensive cosmology remains possible. That knowledge represents something profound, not just data about galaxy distributions or expansion rates, but humanity's attempt to understand the largest structures and longest timescales accessible to observation, to map reality at its most fundamental scales, to document the universe while documentation remains possible. The terrifying void is already here, already growing, already separating structures that will never reconnect. This process began billions of years ago, will continue billions of years into the future. We're witnesses to a cosmic transformation, from structure to emptiness, from connection to isolation, from the middle chapter toward the final state. The universe doesn't care whether we find this terrifying. It simply follows the physics. Dark energy does what dark energy does. Space expands as equations predict. Voids grow as mathematics demands. But we can choose how we respond. We can observe carefully, measure precisely, record thoroughly, share knowledge widely, ensure that what we learn during this era survives for whatever comes after. Because the voids are patient. They have billions of years to complete their work, to stretch space beyond all possible reconnection, to isolate every structure in its own expanding bubble, to transform the cosmos from its current complexity into final simplicity. We have perhaps 100 billion years before the observable universe shrinks to just our local cluster. That sounds generous until you realize it's finite. Until you understand that after that window closes, certain knowledge becomes permanently inaccessible. The cosmic web we photograph today will exist only in records. The expansion we measure now will have carried everything beyond observation. The universe we study will have hidden itself behind horizons that cannot be crossed. This is what makes the void truly terrifying. Not its emptiness, not even its relentless expansion, but the certainty that it represents the future. The inevitability that all structure will eventually dissolve into isolated fragments separated by unbridgeable distances. The universe began in near uniformity. Quantum fluctuations created slight variations. Gravity amplified those variations into structure. The cosmic web emerged. Galaxies formed. Stars ignited. Complexity arose from simplicity. Now dark energy is reversing that process, not by destroying structures but by separating them, returning the universe to large-scale uniformity. Except this time the uniformity is one of emptiness rather than density. We're living through the transition, observing the cosmic web before it fragments, measuring void expansion while boundaries still exist, documenting structure while structure remains visible. This makes our era special, not because we're cosmically important, not because the universe treats us differently, but because we happen to exist when observation remains comprehensive, when the universe's large-scale structure stretches across our sky, when we can still see what's being lost. The voids are teaching us that impermanence is fundamental. That structure is temporary. That separation is permanent. That the universe trends inexorably toward maximum entropy, regardless of what we might prefer. They're showing us our cosmic future, not through speculation, but through direct observation. We can see what awaits all of space by looking at voids today. Empty regions where dark energy dominates, where expansion proceeds unimpeded, where the universe's final state is already manifesting. And perhaps most importantly, they're reminding us that knowledge itself is temporary. That comprehensive understanding requires the right cosmic conditions, that we're fortunate to live when those conditions exist, that this window won't remain open forever. The void is already swallowing the universe, not through destruction, but through separation. Not violently, but inexorably. Not quickly, but certainly. The process has been underway since dark energy began dominating cosmic evolution. Will continue until every structure exists in isolated darkness, until the cosmic web has completely dissolved, until voids occupy essentially all of space. We cannot prevent this, cannot reverse it, cannot escape it. All we can do is observe while observation remains possible, understand while understanding remains accessible, record while there's still something to record. The terrifying void isn't coming, it's here, growing steadily, claiming more space with each passing moment, teaching us that everything we observe today is temporary, that the cosmic web will dissolve, that isolation awaits all structures, that emptiness is the universe's ultimate destiny. This is the reality revealed by modern cosmology, measured through careful observation, confirmed across multiple methods, projected forward through well-established physics. The universe is transforming from structure to void, from connection to separation, from complexity to simplicity, and we're witnessing the transition while we still can.